Hello, GopherCon. I hope you're having a good conference so far. I hope you're going to have a good conference after this talk. And during this talk, I'll do my best. So let's get started. The quest for the fastest deployment time, what does this mean? So the best indicator of a healthy development workflow is a short feedback loop. My point here is that one of the key factors in making sure you're happy as a developer is being able to write your code and very soon afterwards see if that code works. If you have to type a bunch of commands or wait a lot of time, that kind of stuff, you're going to have a bad time. So that's one of the reasons the Go language was created, actually. It's because the compile times of C++ were so large that this was becoming an actual factor into development, into how development worked. And if you ask anyone from back then, anyone who was writing code in the workforce 20 years ago, they're going to tell you that they graduated from college, they wrote their first C++ program, they set it to compile, then they went on, they got married, they had kids, grandkids, etc. And when they were just about to retire, that's when their first program in C++ actually compiled. True story, just ask anyone, really. Now, Go has mostly achieved that goal. Compile times in Go are pretty good. But it's 2020, and you know how it goes in 2020, right? So you can't have a good thing. It always gets kind of out of whack somehow. And so now we have containers and Kubernetes, and they are a big wrench in the works when it comes to having a short development feedback loop time. And that sucks because we solved the compile problem, but now we have other problems, and compilation time is actually just a tiny fraction of the total equation. So what we're going to do in this talk is help you achieve this. So this is a tweet I posted, I don't know, a year ago, almost a year ago. I asked, how long does it take between changing a line of code and that code running in your development cluster? Most people said 30 minutes, and I'm sure they were using CI in their development clusters. I have a tiny rant about that coming in a second. A lot of people said 1 minute, and that is typical for, let's say, if you're not using microservices in Go, which tend to be pretty fast. If you're doing something else, then it's kind of usual that it's going to take about a minute. But it's also the case if you have tiny microservices in Go, but you don't optimize them, you just use basically the typical workflow, you're going to end up with about a minute. And a very small amount of people said 2 seconds. A lot of those were people doing serverless. So that doesn't work for everyone, of course, but my goal here is to show everyone how to achieve around 2 seconds using microservices in Go, running in containers and Kubernetes. So the full workflow, we're not skipping anything, but you're going to have a really good feedback time anyway. So how do we achieve this? And I have 3 rules. One is don't rely on CI during development. And we could argue about this for hours. I have argued about this for hours. Most people agree with me. Some people don't, patience. But here's how I think about this. Development is like writing a book. There's a stage when you need to write the story, you need to switch paragraphs around, you need to create new characters, new story arcs, etc. And that needs to be fast. You have a word processor, and when you want to change the order of a paragraph, you don't have to wait a long time. You just go and do it, and you see it on the screen instantly. After the story is told, you send the manuscript to your publisher. Then they're going to proofread it. They're going to do the galleys. They're going to do the typesetting. They're going to get your editor to do line edits, all that kind of stuff. And then it's going to be perfect for 1 million people to read it. But first, when you're in that initial stage where it's just you trying to figure something out, you want it to be fast. So that's my point. You don't use CI in development. You use CI later. In development, it doesn't work it doesn't do anything. It only slows you down. So that's my point. That's the rant. If you want to argue about this further, there's always Twitter. Second point, use an MDX tool like Tilt, Scaffold, Telepresence, or Garden. So MDX stands for Multi-Service Development Experience. I kind of made up this acronym. And it's meant to describe tools that help you develop in contexts where you have a ton of services. So they might be microservices, they might be a lot of services, but without following the typical microservice structure. They might be basically just a bunch of whatever that are running separately in a like distributed fashion. So there are tools for that. We're going to use Tilt in this talk. Tilt's the company I work for. This is not like a tutorial about Tilt. I'm just going to use it to show off the things I want to do for our Go application. There are other tools you can use if you like. I used to work at Garden. They're pretty competent too. And there's Scaffold, Telepresence, and others that you might have heard of as well. And then the third and most important part is use every hack, cheat, and dirty trick in the book. And the key thing here is you want your feedback loop time to be as tiny as possible. Every minute, every second extra between changing your code and seeing that code live is 1 second where your developer might pick up their phone and look at cat pictures. And when a developer looks at cat pictures, they lose focus from their code. And when they have to come back to that code, it's going to take a lot of mental effort. And you don't want your developers to be mentally exhausted because that's basically the currency they can play with. So every hack and cheat and dirty trick is valid in trying to achieve the goal of making sure your developers' heads don't get tired when they don't have to. Okay, moving on. The goal of this talk is an exploration into how to achieve the shortest possible feedback loop, and I think that is clear by now. So let's see the initial setup. We're going to start with a Go application, and let me show it to you. Here's the application. It's mostly written in Go, except for the React and whatever in the front end. It is an image filter, so I can select an image, I can colorize it, or I can glitch it, or I can do everything at the same time. And the last one is like some machine learning witchcraft that is made so it can label the objects that are in the picture. But this doesn't matter. We're only going to work on the glitch service right now. So we have here a front-end service. We have a storage service. We have each of those buttons redirects the request to a different service. So we have a tiny bit of an example microservice app that we're going to use. And we're going to pretend we are iterating on the glitch service. And that's what we're going to do. Now, next part here. This is running on Kubernetes, and it's set up for Tilt. So like I said, this is not a Tilt tutorial, so I'm just going to give you the basics. What Tilt does is Tilt's going to watch your project, your application for code changes. Every time you make a change to your code, Tilt's going to reply with the appropriate action, and you define those actions. So for example, if I do this, if I change this service, I want to rebuild and redeploy this container. If I change that service, I want to run a specific command, and so on. Basically, it monitors your project and it interacts with your Kubernetes cluster, your containers, etc., in the way that we tell it to. That's what Tilt does, and that's kind of all you need to know. Now, coming back to the slides, it is set up running on Kubernetes, both on Micro-K8s and GCP. So here I have one code base and I have 2 instances of Tilt. So every time I make a change to my code, it's going to propagate those changes into the Micro-K8s cluster running on my laptop and a Google Cloud cluster running, I don't know, on a cloud somewhere. What else is here? Benchmark trickery. This is fun. So you can see here that we have a benchmark button here. So most of these are services that I have running. This is a button that performs an action. This is a button that performs an action. Here I'm just saying this is the local cluster window. This is the remote cluster window. What does the benchmark button do? Let's take a look at this. I'm going to come here and open my Tilt file, and that's how I manage Tilt. So a very brief introduction here. This is a bunch of hacks, so I can use Tilt twice on the same code base. Here I set up port forwards. Docker build is how I manage my images. So I have a glitch service. It uses this Docker file, and this is the context for the image. And I have the same thing here for all the other services. I'm also saying here's all the YAML for all this stuff. And lastly, I have the benchmark button. And all the benchmark button does is it runs this. This script, generate start.shell. So let's take a look at that script. What this script does, it's a bash script, and it generates a Go file. And what this Go file does, let's look at one that's already done so it's easier to see. What this Go file does is we have a timestamp, and this is the timestamp of the exact moment when I clicked the benchmark button. This is going to be embedded in my glitch service, and when the glitch service actually runs in the cluster, I'm going to do the difference. So I'm going to say, how long has it been since I added this timestamp here? So what does this mean? It means I'm going to have a timestamp of when I press the benchmark button. I'm going to have It's been this long since you pressed the benchmark button once the program starts running. This difference is exactly how long it takes between I make a code change and my code is running in my cluster. And that's exactly what we want to benchmark, and that's the time we want to make as small as possible. So let's start with the basics. Let's see the most basic setup that we can have, and that's where people usually start when they go down this road of developing in Kubernetes. I'm going to have a Docker file for my glitch service, and it's the most basic thing in the whole world. There is no caching, there are no fancy tricks, nothing special. I just take a Golang image, I put my stuff in it, I build my code, I build my binary, and I run it. That's all it does. Every time I make a change to my code, it's going to rerun this, it's going to rebuild this image, it's going to redeploy it, and it's going to rerun it. And I already did it here because this takes some time here in the beginning of the talk. The iteration loops are not so fast, so just to save time, I already did it. It took 55 seconds with the local cluster, a minute and a half with the remote cluster. And if we compare this to the benchmarks I did before, it was basically 1 minute and 2 minutes. So we're kind of in the same ballpark. It was a little bit faster right now. On the remote image, it was a lot faster. But that's kind of how long it takes. So what can we do to improve here, actually? So let's take a look at the logs. Is this what I want to look at? No, I think I want to look at the other one. So when we look at this, we can see a bunch of Go downloading. And this means that every time I make a code change, I'm re-downloading all my dependencies, and this sucks. So what can we do? An idea is to use an image layer cache. And this means that here in the Docker file, I'm going to have a separate layer, because right now I'm downloading the dependencies on this tab. And basically, every time I make a change to my code, this tab gets, this layer gets invalidated. I need to download the dependencies again. If I can put my dependencies here, then I'm going to be able to change my code later, and the dependencies are going to still be cached as part of Docker. So that's going to be very interesting. So let's take a look at that. We can do run go mod download, and of course you already need a go mod file. You need to do go mod tidy and all of that. If I do this, now I can come back to my to Tilt. It detected the change. It's redeploying. It's rebuilding. We can already see that go mod download is cached because that's how it goes. And now if we just give it a second, it's going to rebuild, it's going to redeploy, and it's going to be faster than before because we don't have to download all the dependencies again. Okay, so disregard this because the first time Tilt is just setting things up, and once it does, then I can actually click the benchmark button to get the exact number. So let's just give this a second. And okay, almost there, almost there. One more second. And I hate the beginning of this talk because the first benchmarks are quite slow. So then I have to be like stalling and waiting and saying useless things just to keep you entertained. But okay, it's done. Now I'm going to click the benchmark button so I can get the precise measurement. And in the meantime, I'm going to introduce you to my Gopher family. So here I have a bunch of Gophers that I got at a bunch of different GopherCons. So I think this one came from GopherCon San Jose. Is it San Jose? San Antonio? It's the name of a saint and it's in California, you know, the last one. This is from there as well. This is from Colorado in the year before. This was like some toy that you would put an LED inside and then it shines. And these guys at the back, they are from, I think the Go Berlin meetup, including this one that you couldn't see because it was hidden. And that's because in the Go Berlin meetup, every time you give a talk, you get a Gopher. And I've given a bunch of talks, so I got a bunch of Gophers. So that's cool. Now, let's come back here and see if things are already working. We can see that it took 28 seconds this time. Locally and 53 seconds remotely. So this is faster than before. I'm going to look at the benchmarks that I prepared beforehand to see how fast it was. So usually you're going to get about a 50% improvement from your initial setup, which is pretty cool. But there's an issue here. So when you're doing this image layer cache, you have a problem. And that problem is every time, let me go big on the screen here. Every time you make a change to any dependency, it's going to reset that whole layer. You're going to invalidate the whole layer. So if you have 1 GB of dependencies, you change 1 MB of dependencies. If you're using this kind of caching, you're going to lose the whole layer. You're going to have to download the whole gigabyte again. It's not ideal because it takes time, and time means looking at cat pictures, and that's bad. So what we can do instead to make this incremental is just use the vendoring, the typical Go vendoring, because then if I add or remove a 1 MB dependency, that's all that changes and everything else remains the same. So let's try that next and see how that works. And that's going to be pretty easy. I just have to come here. I can, oops, no, that's not what I wanted. I can copy my vendor directory. And then here, of course, I prepared the vendor directory beforehand, so we don't have to do it right now. But let's see here how this works. So Tilt's going to rebuild it. Of course, it needs to get everything in place first, and then I can benchmark it. So it's going to take just a minute. I think I'm going to move on and just show you the results, because this is going to take a while. Is it going to take a while? I'm not sure how long this is going to take. Maybe it's going to take just 30 seconds. So let's wait, and then I'm going to click the benchmark button, and then we move on with the slides. Okay, and of course the remote one takes some time. So if you're not sure why when I'm using the remote cluster it takes longer, it's because then I have to send images up to my cluster. And I use this very terrible phone internet that's actually shared with the apartment. So my internet's pretty bad, so it takes a while. So if you have really good internet, it's probably going to be a lot faster for you, but I don't, so it takes longer. So it's just something for you to know. Here, the remote version takes a lot longer, but that's because my internet's bad. In your case, the difference might not be that big, or if your internet's even worse than mine, the difference is going to be a lot worse. So something for you to keep in mind. Okay, so now I can click benchmark to get the precise times. And let's give you some spoilers, and I'll just show you what happened. So here I have vendoring, and the result is basically the same as using the layer cache. But generally, in my experience, having presented this content a bunch of times, layer cache tends to be a tiny bit faster in general. So that is good. But because of that whole issue where you change a dependency, you lose the whole layer, you have to download everything again, I prefer to pay a tiny tax and just use vendoring. It takes just a tiny fraction longer, but then you don't have that issue. So that's why I prefer it. So let's come here and see the results. 22 seconds, so it was actually faster than before. And remotely, it's still running, so just another minute. 49 seconds. Yeah, so vendoring was faster in both in this case. That is very much not my typical experience. Usually vendoring takes a bit longer than using the image layer cache, but you know, computers are not deterministic. Everything is a big mess. So let's move on. What can we do here? We're caching only dependencies. And like I said in the beginning of the talk, one of the really cool things about Go is that compile time is basically instant. Well, it can be depending on what you're doing. If you're doing very tiny microservices, it's basically instant. Of course, if you have more convoluted stuff, then it takes longer. But the thing is, Go relies a lot on a compiler cache to make things fast. And here we're rebuilding and recompiling from scratch every time, no compiler cache. So basically our compilation time is taking as long as it possibly can every single time. So let's fix this and let's make sure that we can use the compiler cache in this workflow. Let me show you how to do this. And this is something that I had been discussing with friends and stuff for a couple years. It was not possible until some time ago, which sucked. But and like I presented this talk before. I did a bunch of hacks and stuff to try to make this work. The hacks didn't work because then you're moving a compiler cache around. It's a ton of very tiny files, a lot of I/O. It's bad. But now there's this really nifty trick that's gonna fix everything for you. So you can do this very easily, but you're gonna require some experimental syntax for your Docker file because this is crazy hacks territory. And what are we gonna do here? Okay, I'm gonna need mount type cache. And the target needs to be, I think the default directory is this. Let's see if this works or if I'm gonna have to cheat and look at my notes. So we're doing the thing again. It's gonna take a tiny bit of time, and then I'm gonna have to wait and then press the benchmark button again. So let's see how that's gonna go. And I keep thinking of telling some silly computer jokes while we wait for this. But then I'm thinking, like, if I tell you a UDP joke, you might not get it. If I tell you, do I need to refresh this manually? Well, let's just press the button, see what happens. If I tell you a TCP joke, I might have to tell you again. So I don't know. Is this joke thing even worth it? So let's just give it a second and wait for it to do its thing. Let me get the right slide here. Okay, compiler cache. And this is taking a long time. I'm worried. Did I mess up the demo? We'll see. We're already pushing here. I think this is going to take longer than before, which is annoying. We'll see. 30 seconds. I think I didn't have the compiler cache here yet when I ran this. So let's wait a second here and then run it again. And should I skip this? Should I do just the spoilers again? I'm not sure. Yeah, okay, let's do that. So I think this was a tiny bit faster than the last time. Or was it? I'm not sure. Okay, let's just run this again and see how long it takes the second time. I think it's going to be a lot faster because this should not take whole seconds to run. This should be almost instant. Okay, it was faster this time. So it's going to be a bit faster now because we have the compile cache inside the container using the magic of BuildKit. Okay, 19 seconds. This was a lot faster than before. And on this side, it's going to be faster too. But of course, I need to push the image, and that's what's taking so long, pushing the whole image. So let's wait just a second for it. Deploying. Pod rollout. So Kubernetes is kuberneting. 39 seconds. Okay, so this was pretty fast compared to before. So compiler cache, it was 17 seconds, 53 in the benchmarks I had prepared beforehand. It was a lot faster here. It was just 39. So that's interesting. Anyway, the point is using the compiler cache, you get things that are a lot faster than if you're not using the compiler cache. And I suppose that's pretty obvious when you think about it. But let's see how we can improve here. So all this building and shipping containers is taking a very long time. As we can see, now our dependency stuff is cached. We don't need to worry about that. Where is the compiles tab here? I don't know. I saw the compiles tab here. Where is this? Okay. So my vendoring stuff is cached, so that is pretty much instant. The compilation stuff is cached, so that is pretty quick. I'm losing a lot of time with this, pushing containers. So I need to build the container, then I push the container, I have to deploy the container, and then Kubernetes needs to do the Kubernetes. And all of this is taking a long time. So here's another idea. What if we don't have to do this whole container dance? What if we just, let's say, you start your day, you build your container, you're working on code, you're not working on Kubernetes, you're not working on Docker, you're focused on code. The only thing you care is, I'm going to write new code and I need the new code to run. You don't need to update container specifications. You don't need to update Kubernetes specifications most of the time if you're a developer. You only do that every once in a while. So what if we can just keep the same container there and we just change the code that's running inside that container? So yeah, that's what we're going to do next. We're not going to rebuild containers anymore. Every time we make a code change, we're not going to redeploy anything. We're going to keep the same stuff running. We're just going to refresh what's in it and what's running in it. So let's do that. To do that, we're going to need a new feature here that is a part of Tilt. And it's also present in the other tools. So, you know, this is not a Tilt vendor pitch. I'm just going to show how to implement it here. I think it's live update. It might be live reload. I don't know. If it gives me an error, then I'll fix it. And I'm just going to say that when I change anything in the glitch directory, I don't want you to rebuild this image. I just want you to sync that stuff with what's inside my container. And that's pretty simple. So I'm going to do this. I'm going to come back to my Tilt file. I'm not going to need this anymore, but I'm going to need something inside the container watching the code in the container, because the code inside the container is going to change. And I need something to see, okay, we have new code in here, we need to recompile and rerun. So we need a tool that watches files, and a very nifty one is called Enter. And I've been talking about Enter for years, and I really love this tool. So I'm just going to add it to my container here. And then in my commands tab, I'm going to say, take all the files, take all the Go files inside my code base here, pass them to Enter. And whenever any one of those changes, we're going to run this recompile.shell script. And if you don't know what that script is, oops, no, it's not where I want it. Okay, here. If you don't know what that recompile.shell is, it's just this. It's just say, hey, I'm compiling, and then it compiles, and then it runs the compilation result, and that's pretty simple. So what can we do next? Let's see if Tilt has picked up this change. I think it has. Now let's benchmark it and see how long it takes. And compiling, and it took 2 seconds. And remotely, it's gonna take, how long is it already running? Where's the compiling? It didn't tell me how long okay, I'm gonna run this again. Let's just see. 15 seconds, no, this is wrong. Okay, this was the one before. So now it took 5 seconds here, 2 seconds here. Why was it a shorter time the second time? Because now we have a compiler cache. So 2 seconds, isn't 2 seconds the time I promised you in the beginning of the video when I showed you that tweet? Some people take half an hour, some people take a minute, and the really cool kids take 2 seconds. Isn't that what I showed you? Isn't that what I just delivered? Yeah, so let me do a special effect here. Oh yeah. Yeah, this was a mic drop using a different mic because this one's attached. And yeah, cool. If this were a real talk, I would be very happy right now. I mean, if this was a live talk, I would be real happy right now. I am real happy right now, but I can't see your faces. I can't see how impressed you are with my prowess here. So let's just keep moving. This is really cool. Let me go back to the slides. So we're hot reloading the source code. The time is a tiny fraction of what it was in the beginning. This is great, but we have a pretty bad issue here that didn't happen this time, but it might happen. And the issue is that, well, there are 2 issues. So one issue is we have all the Go tooling here, and you usually don't want the tooling in your production images, and that's going to mean you're going to need to have a separate image for development, and that kind of sucks. You can make it work, you can do a bunch of layering stuff, and it's fine, but it's kind of annoying, so maybe you don't want that. And the other issue, and that's the most difficult to solve, is that if you have, let me show you something. I'm going to do here. This is the YAML file for my glitch stuff, basically in Kubernetes. If you have 5 services in your app, this is not a problem because you can make every service have all the processing and memory it needs. But if you have 50 services, every service is going to need to be very tiny and have just a tiny bit of memory and just a tiny bit of processing. And when you don't have enough memory and enough processing, compilation takes forever. So let me show you this. I can do here resources, limit, CPU, 500 megs, 500, well, millis, or however you pronounce that. And when I do this, now it is Tilt detected the change, it updated, and I'm compiling. And well, let's just see how long it takes. Remotely, it's going to be the same. I don't think the containers have the same amount of processing and memory locally and remotely. I didn't check this remote cluster that I'm using, but it's going to get stuck in compiling, and it's going to be compiling for a while. So let's just wait for it to get, okay. They're both compiling. So I'm going to move on with the talk because this is going to take forever, and we're going to come back here later and see if they finished. And they won't have finished. So if you're trying to hot reload, if you're trying to recompile inside the container and the container doesn't have a lot of memory and a lot of processing, it is going to take forever. Yes, forever. It's going to take the heat death of the universe to finish compiling. And that's annoying. We don't like waiting. And To wait until the heat death of the universe, you would need a lot of cat memes to get through. We don't have enough cats on Earth, I'm sorry. So we need something different. Or maybe if there's the case that you don't want this workflow, because maybe it works perfectly for you, but maybe it doesn't. So if it doesn't, we're going to need something different. So here's another idea. What if instead of syncing the source code and compiling inside the container, what if we make use of something we all have, and that's a computer? So if you're using microservices with Go, they're pretty fast to compile. You usually work on one service at a time, so you compile one at a time. Your computer is pretty capable of doing that compilation in a reasonable time. Usually, your computer has a lot more resources available than one container in a whole application that has 50 containers. So let's do the compilation locally in our localhost in our computer, and then we just sync that binary inside the cluster. So let's see how to do that. So we're going to compile locally and hot reload the binary. And this has ups and downs, so let's see what's good and what's bad about it. How do I say this? Is this done? Yeah, it took a billion years. I'm gonna just click benchmark again here, just to see if we can get like an actual measurement of how long it takes, so we can laugh at it. And wow, 6 seconds, 8 seconds. That was fast. I was expecting it to be a lot slower. Anyway, it is a lot longer than what we had before. So yeah. Actually, is it? How long did it take the last time I did this here? 5 seconds? Huh, interesting. Okay, let's pretend this took a lot longer, because every time I did this before, it took a lot longer. So this is just, you know, the demo gods being angry at me. Anyway, let's move on to the previous idea and do the compilation locally and sync it back into the cluster. So what I need to do is I'm going to go to my tilt file where I say what I want to happen every time. I don't want to sync all this stuff anymore. I just want to sync a binary. So I don't need all of that stuff in my container. I just need a binary. Same thing here. I just need a binary. And here I just need a binary. Yeah, I'm going to repeat that a lot later, in this stage. Now let me come back, not this. Let me come back to my Docker file. Nope, not this Docker file. Glitch.docker file. Okay, so I don't need my tooling anymore. I don't need to copy a bunch of stuff anymore. All I need to do is add a binary here, and then enter is not going to monitor any source code. It's just going to monitor one binary. Whenever that binary changes, it's going to, nope, Vim is hard. It's going to run that binary. So inside the container, I have enter. Enter is always running. It watches a binary. Whenever that binary gets updated, it kills the old version and it runs a new one. And that's all that happens here. But now I need this tab to recompile stuff inside in localhost, because before I was using that recompile script to recompile inside the container, but now I want to recompile in localhost. So I'm going to come back to the tilt file. I'm going to add another local call here. And here's what I'm going to do. It's going to be called recompiler. It's going to do a bunch of stuff. So let's just say it's going to echo recompiling. And then it's going to run whatever compilation stuff I add here. And this is just a tiny hack I'll explain in a minute. And this is only going to run when I change my start.go file. Usually you would put a better list here of all your Go files, and you can make this, you can just code this so you don't have to do it by hand, but you would basically depend on any changes to the directory of your source code. Here I'm just going to use start.go because that's the only thing we care about in this benchmark. Now, because I have 2 instances of tilt running and I don't want to recompile it twice, I'm just going to make it only recompile once, and then it syncs to both anyway, but this is just a tiny hack, so you don't need to worry about this. So I'm just going to say if build, then compile is going to be cgo enabled equals 0. I'll talk about this in a second. I'm going to have go build. I'm going to build my, well, I'm going to output this to glitch/main. And I'm going to compile anything that's inside the glitch directory. I think that's it. Let's see if this works. And I'm gonna need one more thing here because I forgot, so I need to have this declared beforehand because hacks. Okay, this might work. Let's see. Nope, I made a mistake on my tilt file. What did I do? Line 62. Line 62. Here, what did I... Oh yeah, I forgot the parentheses. Okay, so back to glitch service. Let's see how long this is gonna take. All right, and let's just wait for the first update and then I can benchmark it. Okay, now I'm going to benchmark. And 2.3 seconds locally, and remotely it's going to take a bit longer because now I need to send a whole binary across the network instead of just a very tiny source code file. So things to pay attention to. Here you can see that we are only syncing one file. We are not syncing source code anymore. And here it took 2 seconds because locally it doesn't matter the size of my binary basically. But remotely, if I'm sending this up the internet and I have very bad phone internet, sending this, I don't know, 15 megabytes binary, it's going to take a couple seconds, and that gets added up here. So let's come back to the slides. Generally, it is about the same time locally. It usually takes a tiny, well, there are hacks here, so let's pretend it's the same time locally. Remotely, it's going to take more because it sent that binary up the network, and that takes some time. So if our bottleneck here is the size of the binary, let's make the binary smaller. And one more thing here. I actually need to show you this because it's just mean. It's just one of those container things that will drive you crazy. So if I remove this, cgo enabled equals 0, let's see what's going to happen here, and everything is going to go up in flames. It's saying no such file or directory. It's going to say the same thing on the other side. Does this mean that I don't have a main file there? No, I do have a main file there. I can come here and I can see. I can see that the main file is here. It was just compiled. It's there. Why is my stuff here saying there's no such file or directory? And this is this stuff. It's because if you're running a Scratch container, or well, not a Scratch, if you're running an Alpine container, it has a different what is it called? A C library, like, you know, the whole thing with shared libraries, and what is the name? There's a name for that. I forgot the name, but there's a thing about like system libraries and share libraries, and especially in this case, when you're doing HTTP stuff, by default, Go uses the stuff that is on your Linux distribution. That is different than what Alpine uses, so it's not going to work. So you need to disable cgo for it to work in an Alpine container. And you should look at Jerome Petazzoni's blog series called Reducing Image Size, and he talks a whole bunch about how this whole Alpine versus the other thing works. I used to remember the names of the things, but I forgot. So check out that series if you care about this. But the end of the story is you need cgo enabled equals 0, else you're going to have issues. But if you have this, it's going to be fine. Now, we want to reduce our binary size. So something we can do is remove debugging artifacts. So, oh, I have an error in the slides here, so I should fix this sometime. So what is this? If you ever use a debugger, something like GDB, that kind of stuff, it requires some information to be present in your binary so that you can use it optimally. If that information is not there, it's going to be very hard to use a debugger. But truth is, we don't use a debugger all the time. Usually you know when you're going to use a debugger, but most of the time you don't. So let's just remove all that information from the binary because it actually takes up a whole lot of space. So how do we do that? It's really simple. Well, it's really simple if you remember the command, because the command is not easy to remember at all. But you just add this, you tell this to your compiler, it's going to remove that stuff, and then it's going to be a lot faster. And I forgot to show it to you live. I forgot to show it to you live, but the size difference is basically we're going to have like 15 and some change megabytes for the version with the debugging artifacts. We're going to have around 12 megabytes for the version without those artifacts. So it actually took a shorter amount of time. So maybe just adding those that information there takes time. It's not just about the file size. 1.5 seconds running locally, which is probably the shortest time we're going to achieve here. And when running remotely, 32 seconds. Wow, this is wrong. Let's do this again. This is a fluke. It's a matter of honor now. This needs to be a shorter time. 1.4 seconds locally. So 1.4 is basically instant. It's like you change your file, you save it, you go to Postman or your front end or whatever to see if it works, and it's already there. So it feels instant. That is great. But here it took 18 seconds. I don't know why it's taking so long. It should take less time. Anyway, let's come back to the slides. Generally, it's going to be a small reduction on both, but significant. So we're going to keep it. And we're still bottlenecked, especially in the remote version, by file size. So let's do something a bit unconventional. And so what we're going to do now, it's going to increase the time it's going to take locally, but it's going to decrease the time it's going to take remotely. So you need to know what you're working with. You need to know, do we have more processing or more bandwidth? That kind of stuff, you're going to need to do that calculation to see if the next step is something you're going to want to do. But here's what I can do. There's a tool called UPX. It's called the Ultimate Packer for Executables, and it makes binaries smaller. So a lot of people think you can't compress binaries. They're already optimized by the compiler. When you send them up the internet, it gunzips the packets, so it's fine. But no, you're wrong. We can make binaries a lot smaller. So let's do that. I'm going to say here, instead of calling this main, I'm just going to call this big. And then here on the next step, I'm going to do UPX glitch / big. I think this is the command. And then I'm just going to move I'm going to rename it from big to main. And once I have a new main file, the whole chain of events is going to trigger. So let's just see what's going to come of this. Okay, I just needed to update first and then I can benchmark it. Just one moment and I'll have some tea. And now let's benchmark it. So 2.5 seconds locally, so you can see it took a tiny bit longer. But remotely, this is going to be faster. So 11 seconds remotely. This is a significant improvement. We were at almost 20, now we're at almost 10. One thing I want to show you, is it here? Where is this? Not here. Is it here? No, I don't know where it is. Is it here? No. Why? I don't know why the thing I want to show you is not appearing here. So let me try the other one, because these are different types of clusters, the output of the logs is a tiny bit different. Okay, here it is. This is UPX, Ultimate Packer for Executable. I ran it with the -1 option, so it's like the fastest one in terms of processing, but it generates the binary that is not as small as it could be. If you have a super fancy processor, you can use a higher level of compression, and it's not going to take longer. But the end of the story here is I had 12 megabytes, now I have 5 megabytes, 40% file reduction. And that is why my time here is so much smaller than it was before. Meanwhile, here, because I don't have to send things down the network, up the network, I'm just copying files inside my computer, I got penalized because I had to run that file compression, and it takes some time, of course, because it's an extra step. So, coming back to the slides, we can see that it took longer locally. It was an optimization. It was an improvement remotely. And that is basically the end of the story here. So we need to be aware that at some point, using a remote cluster and a local cluster, we're going to need to do different things to optimize for each. And that's what I'm trying to show you here. If we look at the final score, live update is it's always going to give you a good result, but it has those two caveats. One is if you don't have enough memory and processing, it is going to take a very long time. And the second is you're going to need to have the build tooling inside your container, and sometimes that's not something that you're willing to have. If you do the local build, locally, it's going to give you a very, very, very short time. You can optimize it. If your computer is good, if you're not running 2 instances of the thing at the same time, if you're not screen recording, etc., it's going to be even faster. Remotely, it's going to be bottlenecked mostly by your network, by your internet speed. So if you have a very good internet speed, this is a non-issue for you. It's going to be very fast. If your internet speed is very slow, or if your binaries are really, really huge, then you might be better off using a local cluster. Of course, should you use a local cluster or not? That's a very big question. I have a whole video about that I'm about to release in a couple of days. Actually, that I released a few days ago because you're watching this in the future. So check out dex.dev, dex.dev for that video about should you use a local cluster or a remote cluster, which local cluster should you use, etc. But these are the trade-offs you need to know. And one thing that people always ask me, what if I'm using a different language? What if I'm not using Go? What if I'm using Python or Node or something like that? And rule of thumb is, if you need to compile something, so that's going to be Go or, I don't know, C or even Java because it has that build step, then what I showed here applies. If you're using a dynamic language like Node or Python, then you're just going to use live update, and this whole local build stuff doesn't exist. So just use live update, and that's going to be very fast, very snappy, and you're going to be very happy about it. But for Go, these are the trade-offs we need to think about. This is what we need to keep in mind. I hope this talk was really useful to you. I hope you learned something new here. I hope this is going to help you be a happier developer because you're going to spend less time waiting. And if you can roll this out to your whole team, that's going to be even cooler because you're going to make a whole lot of people happier. So that's it. Here's how you can get in touch if you'd like. Feel free to reach out to me, especially on Twitter. It's the place I'm most active on. But the other ones are an option too. And that's it. Let me know what you think. If you have any ideas that I didn't think about in this talk, please let me know because I'm kind of a fanatic when it comes to this subject. And that's it. I hope you're going to have a really good time in the rest of the conference. I hope you enjoy the other upcoming talks and see you next time. Bye-bye.